Let's start the summary lecture. So I selected some of the slides we studied this semester in these topics. So we will start with the workload. So we studied the recommended system as one of the key workload in the data centers. So in the case of recommender system, given the user information like interaction history, we obtain representative vectors. So for instance, by averaging these embedding vectors of watched videos. And then we run MLP. So that's why we need a large capacity memory, and we need to access large amount of data, consuming a lot of memory bandwidth. And after obtaining the input vector, we need a lot of computation. So that's why in the conventional CPU-based system, we have memory capacity problem, bandwidth problem, and compute capability problem. That's why we applied accelerator for this part. But for this part, accelerator is not so helpful. So we need a new memory subsystem. So we studied an idea of moving the boundary between computation and memory, like this one, as in the case of TensorDIM, for instance. But these ideas were not commercialized yet. But the majority of workload is actually large language model based on transformer model. That's why we studied transformer architecture, like this one. So we stack transformer blocks vertically to build a large model. Inside of each transformer block, we have attention layer and feedforward network. And we generate the output in an autoregressive manner like this. So the previous output becomes the last input, and we execute the model to generate the next token, output token. But on each transformer block, the input vector goes through attention layer to obtain the output vector. Inside the attention layer, we use KV cache. So the result of previous vectors, actually. For the current input vector, token vector, we calculate query key and value vectors. So in the case of value vectors, we insert them to KV cache. And using the query vector, we do attention operation, vector dot product operation to obtain scores. After normalizing them, we use them as weights to do weighted summation of value vectors. And then output projection. That's the result of attention layer. And then we go to the feedforward network. In the feedforward network, we just execute two multiplications, two matrix multiplication, matrix vector multiplication to obtain the output. So as we saw in the attention layer and feedforward network, basically given an input vector, we do matrix vector multiplication. So in the case of attention, we do matrix vector multiplication to obtain query, key, and value vector. And then attention operation actually consists of matrix vector multiplication and another matrix vector multiplication. So matrix vector multiplication is the primitive operation in large language model execution. But when we generate the output, actually for each output, we execute the entire model using all the input data up to that point. But if you see the compute characteristic of large language model, actually we see two stages, prefill and generation. In the case of prefill, since we already have all the input tokens, actually we can process them in parallel. Even though from the viewpoint of each input vector, matrix vector multiplication everywhere. However, since we can process multiple input vectors in parallel, actually the computation characteristic becomes matrix multiplication, which means we can benefit from parallel computation and data reuse in the case of preview. However, in the case of generation, we return to the original behavior of matrix vector dominated computation. So again, in the case of preview, we do large matrix multiplication. But in the case of generation, matrix vector multiplication. In addition, while generating the output, the KB cache continue to grow. So in the case of long output generation, actually the KB cache size can be much larger than the model size. So we have the memory capacity and bandwidth problem, mostly due to heavy cache in the case of long output sequence generation. So in order to run large language model efficiently, we developed several important optimization methods. First, in the case of paged attention or VLLM, we wanted to avoid worst case memory allocation. So instead of allocating large amount of memory resource for the longest output generation, we just allocate the memory resource only when it is needed, as we allocate memory resource in the case of conventional memory allocator of the operating system. So we allocate memory resource in a lazy manner. So we can improve the utilization of memory resource. As a result, we can actually use larger batch. But when we handle large sequence, long sequence, we face a new problem of large attention score. So in order to handle large attention score, we apply tiling, which we usually apply to the case of matrix multiplication. So instead of calculating the two-dimensional attention score, we calculate the attention score here, and we do computation for attention, but the result will not be the final one because we do not know the denominator of softmax. But when we obtain the denominator of the softmax, actually we have only to do additional division of the previous result. So that's what we do in the case of fresh attention. As a result, we can avoid read and write operation with large score data. But in the case of original large language model execution, basically matrix vector multiplication, as I mentioned in the beginning. So in the case of matrix vector multiplication, we cannot reuse the elements of matrix. So we try to reuse the elements by applying batching. So batching, serving multiple user requests in parallel. So we can reuse parameters in the case of batching. However, we cannot reuse KB cache. That's why we devised another idea called speculative decoding. In this case, we obtain the draft output. And then by running large model in a batch mode, actually we can verify each output and we accept the output until they are correct. So if we have wrong output here, we stop, we accept these outputs and we use the large model output here. And then we repeat this process of generating draft and checking the draft. But here the benefit of speculative decoding actually comes from this moment. In this moment, even though we run large model, actually we have the situation very similar to the prepare. In the case of prepare, we already have many input tokens. So here we already have several input tokens, as in the case of prepare. So that's why, even though from the viewpoint of each input token, the computation is matrix vector multiplication, but overall we have matrix multiplication. Even though the input matrix is skinny, the number of columns is small. In this case, the number of columns is only 4, but it's better than 1. So speculative decoding actually enables large model to reuse both parameters and KB cache, as in the case of refill operation. But in the case of speculative decoding, actually the draft length cannot be so long, like 100 or more than 10 is very hard to achieve. So usually maximum 8. But we want to go further. So to do that, currently diffusion models are being actively studied. So in the case of diffusion model, again, we want to have computation characteristics similar to the case of prefill. So we want to reuse both parameters and KB cache. And we studied training. So in the case of large model training, we need to run many GPUs in parallel. To do that, we need to distribute parameters across many GPUs, and then we need to run them in parallel, but we need communication between them. So here you see how we divide the entire model across 64 GPUs in this example. So we have data parallelism based on zero technology, as you know, and then on each data parallel length, we apply pipeline parallelism. Inside of each GPU node, actually, we apply model parallelism. So in order to do parallel execution of large model, we studied several types of parallelism: data parallelism, model parallelism, pipeline parallelism, and zero DP, and context parallelism as well. So when we compare different parallelisms, so if we compare the two, in the case of data parallelism, originally we should be able to store all the parameters on a single GPU, but the single GPU memory size is very small. So we need a technique of zero DP to realize data parallelism. And in the case of model parallelism, the problem is we need to communicate large amount of input data between GPUs in training. So during training, the input data size on each layer is very large compared to the model size. That's why we do not apply model parallelism between GPU nodes, because the communication bandwidth between GPU nodes is very low. However, inside of GPU node, between GPUs, we have NVLink. So we usually apply model parallelism inside of GPU node when we benefit from NVLink. But pipeline parallelism can reduce the communication overhead by doing communication every n layers, not every layers. So we studied an example of model or tensor parallelism applied to the feed-forward network of a transformer model. So in this case, we execute 4 GPUs in parallel to execute this one. But as I draw figure here, so actually at the end, we need an all reduce operation to obtain the final output vector. right? So this is a model parallelism. In the case of model parallelism, we need to communicate the activation data between GPUs. But in the case of training, the amount of activation data is very large. However, in the case of inference, usually the amount of input, the amount of activation data is much smaller than in the case of training. Because in the case of inference, we use small batch, sometimes single batch. The reason why we cannot use large batch in inference is due to long user latency. So in order to form large batch, so the early user requests may wait for a long time, incurring long user latency, which is not desirable. That's why usually batch size is very small. And in the case of 0DP, actually we apply data parallelism, but we do not have enough memory capacity. So that's why when we execute one model, one layer during forward pass or backward pass, the same. Before executing one model, one layer, we need to do all together with model parameter between GPUs. So temporarily, each GPU has all the parameters of the current layer, and we execute that layer to obtain the output. After that, we discard the received parameters. So we keep only small portion of parameter, and we repeat this kind of operation. Simply speaking, before executing one layer, we do all together with parameters. So this is the overall flow of fully sharded data parallel training. So actually here we divided all reduce into reduce, scatter, and all gather. So in order to avoid redundant communication between GPUs. And we also studied context parallelism, which is important when we need to store a large amount of KV cache. So when we handle long sequence, we need a large KV cache, right? But if we apply context parallelism, as you can see in this example, each GPU keeps the KV cache of 4 tokens, and this GPU gives KV cache for these 4 tokens. However, in order to do attention operation, each GPU needs all the KV cache. So, as in the case of DP, the 0DP, in the case of 0DP, we exchanged model parameters between GPUs. But in the case of context parallelism, we exchange KV caches between GPUs, the KV cache of the current layer. So that's the basic idea. So after doing attention, this one will discard the received KV cache. So that's why each GPU has only to keep half the KV cache, not the entire KV cache in this example. And we studied the data center architecture, mostly focusing on NVIDIA solution. So the recent NVIDIA solution consists of different types of racks. So in the case of CPU, GPU rack, the basic unit is this tray. And inside of this part here, this one, this board actually, this board can be represented in a simple figure like this. So here, the key thing, there are 2 key things. So besides the CPU, we have very large DRAM. And this DRAM can be accessed by GPU program using very high speed interconnect. That's the basic idea of this architecture. And by using 2 boards on a single compute tray, we have this design. And by using 18 compute trays, we actually have a rack. So inside of this rack, we have 72 GPUs because on each tray, we have 4 GPUs, 4 by 18, 72. So between 72 GPUs, we have NVLink connection like this. So we have high-speed connection between 72 GPUs. So in the conventional GPU system, one node has 8 GPUs. Between them, we have NVLink. Now we have much larger NVLink network between 72 GPUs. But the trend of increasing NVLink network will continue according to NVIDIA roadmap. So in the next generation, they may use more than 500 GPUs in a single NVLink network. So in the case of large NVLink network-based GPU system, the parallelism design may change. So the model parallelism, for instance, previously we could use model parallelism only inside of GPU node between 8 GPUs. But now you can use model parallelism between 72 GPUs. And in the future, you can use model parallelism between more than 500 GPUs because the NVLink network continue to grow. And the data center also needs large storage in order to keep large KV cache. And so now the data center size is very large in terms of the number of racks. So their communication need to be very fast. So that's why now we exploit optical communication for the inter-rack communication. But as you know, in the near future, even for intra-rack communication between trays, we will use optical connection. And we studied accelerator, but basically we use accelerator to do matrix-matrix multiplication in a tile-based manner. So in the case of GPU, we store one matrix in main memory, DRAM, and the other matrix inside of on-chip memory. But the on-chip memory bandwidth is very large compared with off-chip DRAM bandwidth. That's why in order to resolve the problem due to slow off-chip memory, we try to reuse the data we read from slow memory as much as possible here. So that's why after reading one tile from slow DRAM, we try to reuse the tile data again. In this case, we use the same tile data 4 times. But even when we reuse the tile data, if we have some idle time, still the memory is the bottleneck. So we need a method to reduce the memory latency or increase the amount of computation. So by using larger matrix, by having larger batch. But in the case of systolic array, it is quite useful in matrix-matrix multiplication. But in the case of generation of large language model, for instance, mostly matrix vector multiplication. So systolic array is not suitable for that kind of matrix vector multiplication dominated case. So in such a case, the dot product based accelerator will be useful. So this is one example of dot product based accelerator. Here we have multiple dot product engines. So we can do 8 dot product operations in parallel inside of this. So each dot product will do dot product of 2 vectors having double dimension. So here we have 4 dot product units. and they have their own local memory. So in order to benefit from parallel computation, we need to partition input and output matrices, and we need to store the partitioned data in a distributed way like this. But this is one of possibilities. So depending on the matrix shape, sometimes we can use all the dot product engine to do large dot product, or if the matrix size is small, so we can run small dot products in parallel. So this kind of reconfiguration is possible. So as a result, we can better utilize compute units in the case of dot product dominated cases, like in the case of matrix vector dominated generation phase. And currently, the NVIDIA provides a new accelerator. So here, actually, they benefit from large on-chip memory bandwidths. So on this chip, they use many small SRAM blocks. They provide large bandwidths, much larger than HBM bandwidths. So here, so this one, 8 LPUs provide 55 times larger on-chip memory bandwidths than HBM bandwidths. So by exploiting such a high memory bandwidth, actually they can accelerate feed-forward network execution. Feed-forward network execution is basically matrix vector multiplication. So by exploiting large on-chip memory bandwidths, actually they can accelerate matrix vector multiplication. So their design, LPU, looks like this. So here they use many on-chip memory modules. So the overall memory bandwidth can be very high. So we store the matrix, the parameter matrix here, and by reading them in parallel at high bandwidth, we can do matrix vector multiplication in a very short latency. So that's why they proposed partitioning the generation operation, prepare LLM execution in this way. So on GPU, they run prepare. For generation, they run attention here, but feed-forward network on this Groq LPX lag by exploiting large on-chip memory bandwidths. So as I draw here, so actually we do matrix vector multiplication on feed-forward network. So by doing matrix vector multiplication on one LPU, by doing this part of matrix vector multiplication on another LPU, actually they can run, in this example, 4 LPU chips to do one matrix vector multiplication in parallel. And we also studied the possibility of having 3D stacked DRAM. So in the case of LPU, we could benefit from large on-chip memory bandwidths. That's good. But the limitation of on-chip memory is the capacity. So we have very small capacity actually. So ideally we need large capacity, large bandwidth memory. And that's why 3D stacked DRAM will be studied, actually will be commercialized in the near future, because 3D stacked DRAM can provide large number of wires. Currently, by using new packaging technique called hybrid bonding, we can have large number of connections between DRAM silicon die and logic die. So the number of wires actually determine the bandwidth. So by having more wires here, more connections, we can increase the memory bandwidth. In order to increase the capacity of memory, so in this paper, they propose using monolithic 3D DRAM. So on a single DRAM die, by having multiple layers of cells, as in the case of vertical NAND, we can increase the capacity. So this is a research proposal, but hybrid bonding is now being commercialized. So in the case of HBM4, actually, the reason why we could increase memory bandwidth in the case of HBM4, basically due to hybrid bonding between memory die and logic die. Even though actually in the case of HBM4, we use hybrid bonding here. So in order to support large number of wires, we need more TSVs, actually. And we studied the conventional idea of CPU and GPU architecture, cache, and memory. So in the case of CPU, we studied out-of-order architecture. So here we have very simplified architecture of out-of-order core. So out-of-order core is based on basically two key ideas. One is additional input register realized in reservation station, and additional output register realized on reorder buffer, right? So by using this one, actually we can avoid write after read hazard, actually. But by using additional output register, we can avoid write after write hazard, and we can also benefit from speculative execution. And in the case of GPU, the basic function of GPU is overlapping computation and communication by multi-threading. But in addition to that, in terms of memory hierarchy, the GPU currently exploits shared memory, local software-based cache. So in order to use shared memory, we use this kind of statement, and then we read the data to shared memory, and then after all the threads read their own data to shared memory, we start to use the data stored in the shared memory. So the latency here is very, very small. So that's the benefit of shared memory. But as we studied using loop-line model, in the recent GPU, we tend to follow this line. So here we have arithmetic intensity and performance. We continue to increase the effective performance by increasing arithmetic intensity, actually. So if we do not increase arithmetic intensity, actually we will follow this line. But by increasing arithmetic intensity by using larger tile in matrix multiplication, we could follow this line. So we could obtain higher performance than in the case of fixed size tile usage. And we reviewed the basic architecture, basic operation of cache in terms of associativity. And we also studied the relationship between virtual addressing and physical addressing. So in this case, actually we use the benefit of the two types of addressing. So we use a virtual address to access 4 kilobyte cache, but we need actually physical address. So tag comparison is done using physical tag. But power consumption is also very important in using caches. So we developed many low power methods as exemplified here. So by exploiting the fact that we are accessing the data in the same cache block, instead of accessing multiple tags and multiple data array, we have only to access only this data array using that information of accessing the data on the same cache block. So this kind of optimization is commercialized in most of the processes. And we also studied how to use line fill buffer. So basic function of line fill buffer, as the name shows, in case of cache miss, we first receive the cache block data using line fill buffer. But while receiving the data, if the CPU needs the data available here, we provide the data immediately. So line fill buffer hit is actually exploited. But after forming the entire line, we move the line to its position when we have a new cache miss. And in the case of large associative cache, especially L2 and L3 cache, tag access can consume large power. So to reduce tag access power consumption, we actually have two stages. So first we access tag. In case of hit, we access data in the next cycle. But even in this case, in case of highly associative caches, the number of tags will be large, like 16 or 32. In that case, the tag access power will be similar or will be larger than the data access power. So in such a case, we need a method like counting Bloom filter to reduce tag memory access. So in the case of Waveguard, in front of each tag memory, we have small counting Bloom filter. Actually, this one is a non-membership function, as you know. So in the case that we cannot find the tag, this one gives definitely negative answer. So we can rely on that definite negative answer. So as a result, we can avoid accessing this tag array because we cannot find our data here. So that's useless access. We can avoid that kind of useless accesses. So as a result, we can reduce power consumption. But in order to have high performance operation, the cache need to be non-blocking. By non-blocking, as you know, in case of cache miss, the cache continue to receive new requests. In case of hit, it will provide the data. In case of miss, cache will generate another miss request to the memory. So this is non-blocking cache. So by using non-blocking cache, actually, we can access the multiple banks in the memory. So as a result, we can reduce the average latency in mishandling. And we also studied prefetching. So in case of cache miss, we need to access memory or larger cache. So, but by checking the memory access pattern, we can initiate prefetching operation. So to do that, we use two terms, prefetch degree, the amount of the number of cache blocks prefetched, and the distance, the address distance between fetched cache blocks. So if we have large values, the prefetch is quite aggressive. So we can adjust the aggressiveness of prefetch depending on the result of prefetch operation in terms of accuracy and timeliness and cache pollution. And we studied cache coherence problem in case of multiple cache subsystem, and we studied several cache coherence solutions, including a Snoopy solution and directory-based solution. And we studied main memory, usually DRAM, and we studied DRAM cell and DRAM cell operation actually. So we have a low cycle, typically 50 nanosecond. And we studied memory access scheduling, but the scheduling alone may not be sufficient. So we need address mapping to better utilize multiple banks, like this one. Instead of using BRC, by using RBC, we can distribute data across multiple banks. So in such a case, a rectangular shaped memory access actually accesses 4 different banks in parallel, as in this case. So we can reduce the overall latency. In the case of DRAM, we need refresh operation to avoid the performance overhead due to refresh operation. The current DRAM, especially in the case of low power DRAM, we are applying an idea called per bank refresh. So previously, the memory controller issued refresh command to the DRAM. Upon receiving the refresh command, actually the DRAM determines which row to refresh. So the memory controller does not know which bank is under refresh. So during the refresh time, the memory controller could not access DRAM because it does not know which bank is under refresh. But by applying per bank refresh, actually the memory controller knows what happened inside of DRAM related with refresh. So while refreshing one bank, the memory controller can access the other banks. So actually we can overlap refresh operation and memory access. So as a result, we can avoid performance overhead due to refresh. And we also studied an error problem of DRAM called row hammering. So if we continue to open and close a row, their neighbors will suffer from large bit error. They are victim. So the current DRAM manufacturers currently developed their own solution to address row hammering problem. So inside of DRAM, their solution is realized. But traditionally, in order to recover from one bit error in DRAM, we used additional chip. So in the additional DRAM chip, we stored parity bits. So by using those parity bits, in case of one bit error, we could correct the error. But in case of 2-bit error, we could detect the occurrence of 2-bit error, even though we cannot correct the 2-bit errors. But knowing that there is error is very important. In that case, the operating system or system software can do something to recover from the crash. And we also studied processing in memory, like this one. So in this case, we do matrix vector multiplication on memory side using compute units realized on memory die. Okay, so let me conclude the summary lecture. So this slide shows the roadmap of NVIDIA. So actually we can see near future data center architecture. But what's next? It's not easy to imagine the next architecture, but we can imagine next one based on key directions. So they are core technology for new rack scale architecture. Basically, we will use large mainboard because inside a single rack, we should be able to do more computation. We should be able to store more data. So to do that, basically we need large mainboard. And on large mainboard, we can place more silicon chips. But the board size is large. The communication between silicon chips will take long time. So we need a solution to shorten the latency between silicon chips on a single large board. Probably optical connection can be used for the communication on board. But before that, we will use optical connection between compute trace, compute node inside of a single leg, as I mentioned before. But after that, we will consider applying optical connection to the communication on a large single board. And 3D stacking is also very important. So we can think about several possibilities of 3D stacking. So we can stack DRAM and logic dies. So Samsung already demonstrated the feasibility using their own product name called GHBM. And we can also place logic dies on top of logic dies, like this one. Instead of using large two-dimensional silicon single die, by dividing the large single die into smaller ones, by stacking them, actually the wire length between two blocks can be significantly reduced in this case. So that's the benefit of logic die stacking. Probably Feynman GPU or may use logic die stacking. And on a single DRAM die, we can have multiple layers of memory cells. So as in the case of SK Hynix monolithic 3D DRAM. So that's another 3D stacking possibility. And as I mentioned, optics, in the beginning, intra-rack communication, and finally, on a large board, optics may be used. So based on these core technologies, we can think about the possibility of future rack scale architecture. Basically, we may use more GPUs and more accelerators like LPUs, and we will use 3D stacked memory on top of GPU or on top of MPU or LPUs. And probably we can also have vertically stacked logic dies and optics. Okay, that's the end of our class in this semester. Thank you for your attention in this semester.